Do subscribe to Ekeeda channel and press bell icon to get updates about latest engineering, HSC and IIT JEE main and advanced videos.
Now, friends, let us solve question number 26, which is the question number 6 of your physics paper 2 2014 advanced paper code 8. Now, let us start with question number 26. Friends, let us start with the question. The question says, parallel rays of light of intensity that is 912 watt per meter square. So the intensity of light given is watt per meter square, are incident on a spherical body. This is a spherical body kept in a surrounding temperature. The temperature of the surrounding is 300 Kelvin. The body temperature is not given, suppose that it is T Kelvin. Take Stephen's constant as 5, 7, 10 raised to minus 8, because we already know that Stephen's constant is 5.67 and 10 raised to minus 8 watt per meter square Kelvin raised to 4. So now this value is given, and assume that the energy exchange with the surrounding is only through radiation. So there is no loss of energy due to the there is no energy loss due to other processes or other modes of heat transfer. The only process that is taking place is radiation. The final steady state temperature of the black body is close to. So this is a black body, and we are supposed to find the final temperature of this black body. Now this is constantly exposed to this intensity, parallel rays of light of intensity. This is striking. Now if I want to find the temperature, I have to use that equation, Stephen's law. I have to use Stephen's law because that is used here. Stephen's law states that if it is a black body, then Stephen's law for a black body, because it's given black body, Stephen's law says that the emissive power of the body, black body, is proportional to the fourth power of absolute temperature. It's fourth power of its absolute temperature. This is some constant T raised to 4, because black body there is no introduction of the emissivity. Emissivity becomes 1, so it is E equals to sigma T raised to 4. Now E is nothing but the emissive power, which is the amount of heat emitted per unit area per unit time at a given temperature of the existing temperature of the body, which is sigma T raised to 4. If I think of the rate of because final steady state temperature of the body is close to steady state, means that at steady state, if there is a body, the rate of emission, suppose that is R1, and the rate of absorption, that is suppose R2, then at steady state R1 and R2 must be same. This is the previous theory of heat exchange, which says that at any temperature other than 0 Kelvin, at equilibrium, the rate of emission and rate of absorption must be same. and the rate of emission depends on the temperature of the final temperature of the body, whatever is the existing temperature when at constant weight. So whenever that final steady state is achieved, that time the temperature is T. Though I have taken this temperature T, but this is this temperature is the temperature of steady state. This is the temperature of the steady state. Now, if I use that, this is the rate of emission, and that is proportional to T raised to 4. That depends on the temperature of the body, and this one depending on temperature of body, but this one rate of absorption depends on the temperature of the surrounding. Suppose that is T naught. So that AT, this is AI you can multiply over here, AI can multiply over there. This is for emission and this is for absorption. This is sigma T naught raised to 4. Then that difference must have been absorbed because that temperature has been increased from some initial value to certain value, and by doing so its temperature increases and the rate of emission and absorption becomes equal. Now if I want to write that, then I will write this expression of sigma T raised to 4 minus this sigma T naught raised to 4. This is the rate of loss of heat, or that is radiated to the surrounding, rate of loss of heat. That must be equal to the 912 value that is given in the question. Okay, and that divided by 4. So from here sigma T raised to 4 is sigma T naught raised to 4 plus 912 divided by 4. This is if I divide sigma, then T raised to 4 is T naught raised to 4 plus 912 divided by 4 sigma. If I put the values T naught to 4, T naught is 300, that is given surrounding temperature, and this is 912 divided by 4 sigma. Sigma is 5.67 10 raised to minus 8, and this comes out to be 12 10 raised to 8, and this is 3 raised to 4. You have to solve that. 3 raised to 4 is 9, and 3 is a 9, 81. This is 81 plus 912 10 raised to 8 divided by 4 into 5.7, because that is given as 5.7. So now we have 912 10 raised to 8 4 into 5.7. Now if you take 10 raised to 8 common, this becomes 81 plus 912 divided by 4.5, 4 into 5.7, because that is given as 5.7. This is not 5.6. It's okay. Then I have to solve this, and then this becomes 10 raised to 4. If I solve that, how much I will get? If I use that calculator, this comes out to be, let us see how much I am getting that. This I am getting as 912 this is 912 divided by 5.7, that is 40. So 81 plus 40. So this is 121 into 10 raised to 8. If I take the root of that, fourth root, this becomes t equals to 1 to 1 10 raised to 8 to the power 1 divided by 4. Now this becomes, this is 2 and this is become 1/4. It's 3.3. Okay, then this comes out to be 330 Kelvin. This comes out to 330 because this is 100 multiplied by 3.3 is because 3.3 4 times is 121. You can see here 3.3 into 3.3 into 3.3 is around 1 something like that. So it's approximate result because we are concerned with the temperature of nearby temperature. It might be a little less than that, it might be a little more than that, but we are not concerned more about that because the difference are very large. So 330 is obviously here. Even if you are getting 320 or 328 or 335, then also this is the answer because there is no other options nearby this. So this is the correct answer to this question. Okay, thank you.